Mm-hmm.
Physics was important. It was just plug in.
Let me check. Oh, my goodness.
So we said there were 3.
Wait, Dr. McGuire, how many, I saw that there are like 5 lab reports open now. Did you want all 5? Or the 3 we discussed, 2, 3 we discussed?
I want the phase diagram.
Mm-hmm.
Okay.
What isn't truly easy was the titration curves and the indicators. Did I even make that one a report?
Good question, I don't know. I
We
didn't
have
know.
2 titrations open.
The carbonate bicarbonate,
Okay.
because the math there is,
Important.
well, it was on your test about I've got 2 things and I'm really only measuring 1, but I know that there's only 2 things, so when I measure 1, I know
Oh,
that
it was
the
that
other
thing.
thing is
Okay, I was gonna
unmeasured.
mention that one if you could.
Yeah. So there's a math there, I want that one. And then,
Battery? You posted the battery. I don't wanna do the battery, not gonna lie. Love it right now.
concentration cell.
Okay, I already did it last semester. I can do it. I can do it all day long.
Copy and paste. No, I'm just kidding.
Literally. I deleted all my lab reports. How can you these again? Or the name of them. Oh well. Oh yes. We're on the 3rd one.
So we have 3 cases. The contaminant is a non-volatile, non-electrolyte. The contaminant is a non-volatile electrolyte. That's kind of an ionic strength thing again.
Yeah.
And then this last one, we have a volatile mixture. And here's where we see ideal versus non-ideal solutions. Raise their head. Here's a question. The vapor pressure of benzene, which we will call P0, and then you can either write in the benzene or C6H6, is 95.1 millimeters of mercury. That's higher than I thought. When I look these numbers up, that's pretty good. Benzene, of course, is very carcinogenic and not good for you. It's kind of a difficult, so when we're looking at solvents for reactions, specifically for reactions, this is non-polar. So if we're looking for a good non-polar solvent, this sounds like it. However, its volatility is just wrong. That it is volatile enough. So what you want at the end of your reaction is you want to separate your product from the solvent. And we typically do that by evaporation. And it has a mix of volatility and melting point that it freezes in the flask.
What?
When you pull a small vacuum on it, which would normally evaporate the solvent out, it freezes in the flask.
Interesting.
Yeah. So, not great. Plus the whole cancer thing.
You know, this is a side.
And the vapor pressure of toluene, which we will call P0 C6H5CH3. So condensed formulae here tell us kind of what the structure is.
Benzene with a
Yeah.
Benzene is this fella. And toluene is that fella. It's got a methyl group on it. All right, also highly non-polar and really good solvent. You've all smelled it. That's the smell of glue, paint, industrial solvents. Okay. These are the vapor pressures. And if anything, if you had asked me to guess, I would have guessed them the other way around, but it turns out that, no, that is it. Okay, question. What is the vapor pressure of a mixture when you take 60 milliliters of benzene and 40 milliliters of toluene are combined? Question mark. What's the vapor pressure of the solution? And we'll go ahead and treat this like an ideal solution. I have a mole fraction of C6H5. When I have no benzene, I have no vapor pressure, so pressure is up here, and amount. When I have pure benzene, I get a 95.1. So there you go. It should be somewhere on that trend line. And then I'm going to plot that against C6H5CH3 that goes from 0 to 1 the other way, but is only down here at 28. So if this is ideal, and I'm going what? Which one's the biggest amount? There's more benzene than there is toluene. So I should be somewhere here. Should be somewhere there. And if our mixture behaves like an ideal mixture, well, I have to get a number that is between these two numbers, vapor pressure of the mixture. Well, I say I have to, but it could deviate, it could bow out, or it could sag down. Am I expecting these two to deviate from each other?
Yeah,
Because?
they're volatile. They can
Okay, well. When do they deviate? Deviations from Raoult's law happen when?
Is it like a higher?
If these two molecules attracted each other, then they wouldn't leave the container. If they repel one another, then they would want to get away from each other and they would go into the vapor phase more. So, my black line here is ideal. If they attract, I would see a negative deviation, and my actual value would be somewhere on this line. If they repel, then I would get something on that line. Am I expecting those two to attract or repel?
They're gonna mix because they're both non-polar, but
They're both desperately non-polar. I don't think they're gonna deviate very much from ideality at all. I think this is going to be about as close. Maybe like heptane, hexane, two non-polar liquids. They have no attractive forces, there's no dipoles, there's no hydrogen bonding. If one of them was polar and the other one was more polar, then they would want to be apart from each other. So I'm expecting as close to ideality as we're going to get. Okay, let's go find that number. Yeah.
They repel and realize the pressure behind
Because they're repelling each other where they are, which is in the liquid phase. And they have the potential to evaporate, to be volatile. And if they repel each other in the liquid phase, when they escape into the vapor phase, they could put so much extra distance between each other. So the repulsion basically goes down to zero. Okay? The repulsions are in the liquid phase. What happens in the vapor phase is a consequence of that. If they're attracted to each other in the liquid phase, like they're both polar, we can get dipole-dipole or hydrogen bonding between them, then they won't go into the vapor phase, because as this one's trying to go, the other one will say, hold on, I'm attracted to you. Okay. Vapor pressure of the mix, this is Raoult's law, is the mole fraction of the first component multiplied by the pressure, the vapor pressure of the pure component, plus the mole fraction of the second component multiplied by the pressure of the second component. I'm becoming increasingly irritated with physical chemistry. That pressure is a lowercase p.
What? Is it really?
Yes.
No way.
No, I'm just
Mark,
not
why
gonna,
is this is
I'm-
so sad. Like
I'm
this
just
year,
not
all the
gonna-
terms we
not gonna deal with that.
just no.
Uh,
Let's go back to whatever you were just chill.
I think that maybe collectively, all of the pressures gets to be a capital P, but just the pressure of that.
That's disrespectful.
is a P. All right, how do we find X? It's not really an X, it's a it's a chi, it's a mole fraction, it looks like an X. X of A is the number of moles of A divided by the total number of moles. Okay? Do you have enough information in the question to answer that?
We'll just need a periodic table, but yeah.
You would need the formula mass of carbon and the formula mass of hydrogen.
Wait, is it because we know that milliliters can convert to grams?
Yeah, but how?
They're moles.
They're 1 and 1, 1 to 1, 5.
No.
No. So moles, right? The number of moles of A is the mass of A divided by the formula mass of A. We don't have mass in our question. We only have volume. So the thing that's missing, he hasn't made it on the board yet, is that density is mass divided by volume, which means that mass is density multiplied by volume. So I need densities here.
I was about to say,
I was like, I didn't really want to use moles, because there's a lot of C's and H's and O's.
Density. For benzene, this is a really good quiz question because the two numbers are different from each other, but they look very, very similar. 0.876 grams per milliliter. And here it is 0.867 grams per milliliter.
That would be so upsetting.
Okay. Carbon has an atomic mass of 12 point what?
0, 0, 1. Oh, oops, 0, 1, 1.
And hydrogen has an atomic mass of,
0, 0, 8.
yeah. At some point, you don't have to memorize this, but at some point it just kind of settles in.
It just happens.
Yeah, it does.
It's okay.
Grad school.
Yeah, you'll.
During my graduate school interview, a professor, fairly big one, medium big. He's an OBE. He received the Order of the British Empire. It's like a thing.
Wait, Order of the British Empire?
me a pen during the interview and said, "There's the board, write the periodic table."
I'm crying.
Hydrogen, helium, done. That's all.
Lithium, barium, no, I would put, no, it's boron.
Beryllium.
Beryllium. And barium's a different one, it's in the third row.
Wait, and then is it like when you jump over here? It's not
B.
carbon yet. What is it?
It's B, no, sorry, it's
Now I'm talking about when you
lithium,
jump over
beryllium, boron, and then carbon, oxygen, nitrogen, oxygen. I would have figured it out, cause I was like, oh, there's a 12,
Then
there's not.
no. Then what is that right there? Neon? No.
Neon, yeah.
That's all I can do.
And sodium.
Oh,
Is it
sodium.
Sodium's on the,
Wait,
sodium.
I wrote a great big chunk of it.
magnesium?
Okay.
I forgot all that. Go back down to the one of the
I just taken
calcium,
finals, so
potassium,
I knew what I was
calcium.
doing.
Yeah.
It decays after a period
That's
of
it.
time, but
I
you
know.
can't remember. Wait a minute, is rhodium underneath iridium or is iridium underneath rhodium? It erodes after a while. But I had just taken finals, so I knew what I was doing.
He was wrong for that. Really? What's the point of memorizing the period?
Well, back in his day, they didn't have the internet. We have the internet, so we just look it up all the time.
Go. You have to turn your volume into mass with density. You have to turn your mass into moles by dividing by the formula mass. You then turn your moles into mole fractions, and then you turn your mole fractions into the vapor pressure
Perfect.
of the ideal solution. We're assuming ideality.
Okay, assuming.
It's a ball here.
Come on, I don't want to leave anything on the table today. We've got very little left to do. two numbers?
Yes. And it's on the upper side.
Is it closer to this number than it
Yes.
is to this? Probably right.
Probably right.
Okay, working backwards. Let's do benzene. The other bit's better. Benzene mass
77.
equals density times volume, which is 0.876 times 60. That way we have more than one significant figure. Equals 52.56 grams. Okay. So then moles is mass divided by formula mass. And there are 6 12s, which is 72, plus 6 1s, which is 78, plus your decimals. So this is 52.56 divided by 78. What's the decimal after the 78? Anybody write that down?
78.114.
Okay. Which gives us an answer of 0.674. That's my number without the decimal here. Your number will be a little bit different.
Mine's a 3, so it's
Okay. Well, let's use the real numbers. And then, we have to do it for the toluene before we can get to X. So toluene is the same thing. It is the mass times density. Density here is 0.867. And the toluene is only 40 milliliters, which gives me an answer of 34.68 grams. The number of moles is the 34.68 divided by the formula mass of toluene. So the difference between toluene is it's C6H5CH3. So take one of the hydrogens away, add a carbon, and then add another 3 hydrogens, and you get 92.14. So the number of moles here is 0.376. Okay. So the mole fraction for the benzene is 0.673 divided by 0.673 plus 0.376. The number of moles of the thing you're thinking about divided by the total number of moles. So the mole fraction here is 0.642. And the mole fraction for C6H5CH3 is 0.376 divided by 0.673 plus 0.376. Lots of these numbers look like each other. Make sure you keep them in the correct order. All right, something magical should happen right here. That these two numbers, because this is only a 2-component system, those two numbers should sum to 1.00. That's how it works. Mole fraction has to be a number between 0 and 1.000. those two numbers do. Okay. So, the vapor pressure of our mixture is the mole fraction of the first component multiplied by its its pure vapor pressure, plus the mole fraction of the second component multiplied by its pure pressure. Make sure you use the right numbers. This gets to be 0.642 multiplied by 95.1 plus 0.358 multiplied by 28.4. You should have a number that is between these two numbers. Because we had more volume of benzene, that made us think that we should be here. It isn't actually the number, it's not the volume that's going to decide, it's the mole fraction. Because we had more volume of benzene, and benzene is actually lighter, has less mass than toluene, it definitely is tilted. So our number, somewhere between these two numbers, but should be higher, should be closer to that one. And your number is?
71.2.
71.2. I got 2, but I used a slightly different set of numbers because I didn't, I rounded up here because I did it in the head. Do we get all the points?
No, we are in, milliliters times mercury.
We're in a barometric pressure unit. We're in millimeters of mercury. Barometers work by having a horseshoe-shaped contraption that is open at one end, and your atmospheric pressure pushes down here, and on high pressure days pushes down, forces the mercury around the bend and up here, and there's a resistance against gravity. And so you put a ruler here, and you just measure how high up is the mercury meniscus. Mercury meniscuses, what's the plural for meniscus? Mercury meniscuses are the opposite of aqueous meniscuses because there's a difference in adhesion and cohesion. Very little adhesion with mercury. You get that number? Okay. Then we're good.
Wait, is that it?
No.
Almost.
I was like,
I know, but then you did
I know.
Almost.
We're close though.
We're like,
Didn't bring a watch. There's no clock in this room.
11:35.
Okay.
We have time. Don't.
Time for 2. Okay, these component systems they can be more than 2, but most everything is shown as a 2-component system. If we know what one of them is, then we automatically know the other one. Okay, so here's a kind of a halfway forward, halfway back question. In a butane acetone mixture, where the mole fraction of acetone is 0.577. Has a vapor pressure, but the butane that is 698 millimeters of mercury. What was the value of millimeters of mercury for the previous example?
Oh, like 95.1.
Well, that was for the pure benzene. For the mixture, it was 74. This is much, much bigger.
Yeah, that's a lot.
Well, there's a number in millimeters of mercury that we should probably know. 760. 760 is considered atmospheric pressure. It's not relevant to this question. Well, not it's relevant. That's our conversion factor. 1 atmosphere is 760 millimeters of mercury. And then there's another unit, bars, that sets it to 750. Because 60 doesn't divide into 1,000 the way that 750 does. Yeah. So it's just a little bit off. So bars and millimeters of mercury, also known as torr, are a little bit different from each other. Okay. So acetone we know is a liquid, butane's a gas. This is a gas dissolved in a liquid at this point. There's a very high vapor pressure. Very high vapor pressure. Calculate the pure pressure for butane. This is ascribed to a particular temperature. In the question, it's 20 degrees Celsius. It doesn't matter. If I wrote down 25, 20 degrees, 0 degrees, it doesn't matter. It's not gonna, it's like at a fixed temperature. Okay. Just for clarity, at 20 degrees Celsius, these are the actual numbers, but it's not part of the question. All right. What do we do?
1 minus.
Yeah. Yeah. That XA plus XB has to be equal to 1.00. Our mole fractions are like percentages. Instead of being out of 100, they're out of 1.00. That I have two things in solution, and when I count them up, they have to sum to 1. So what am I going to find?
The mole fraction of
Butane. Because I have that number, but I don't have, and I've got that number, and these two numbers don't match. They're for the different components. So I'm going to go find the mole fraction for butane, which is, all right. Oh, A and B, acetone and butane. That's easy.
That's hilarious. Was that intentional?
No.
I like that though.
Me too.
So there's my 1. Here's the A and the B. What do I do? Subtract what?
1 minus x.
0.5.
There you go. Is that squeaky getting squeaky
Oh
nose
my
getting
god, he's
annoying?
starting it again.
Is what now?
0.433.
2, 3.
Yeah. Units?
2, 3.
None.
Doesn't have units. Dimensionless
4,
property.
2, 3.
Oh, 42. Oh yeah. Sorry, I did in my head.
No, that's good because I wouldn't be able to do it.
There's a YouTube channel that goes around and asks people on the street,
Oh Lord.
hey, what's this? And then they obviously say, like, name a state.
Texas.
There you go, you pass, you win.
No, but the fact that there's
Wait.
so, I've seen those videos, it's kind of scary how much of the, like, name a state, or like, it's like simple, like, questions.
Name
like,
a
or
state, and
like-
they don't know.
Or like,
Yeah, one of his questions is, what's 75 plus 35?
and that's 110.
But everybody says 100,
What?
because they see the 70 and the 30 and they panic and they jump.
And then they forget it.
That's why you didn't get it.
Yeah, and that's why I did, but yeah. I did it every
No, my favorite one was like, where's Korea on the map? And I think people were all like, oh, it's right there. It's like, no, that's China. It's right here. That's India.
Okay.
My geography sucks though. I know where Korea is, but I don't know my geography.
I do know where Korea is. But certain
All right, now what do we do?
Yeah, Middle East.
Yeah, like that good.
Sorry, just don't ask me.
Afghanistan. I know where Saudi Arabia is. That's about it. YouTube?
The previous one said that the vapor pressure of everything was the mole fraction of the first component multiplied by its pure vapor pressure, plus the mole fraction of the second one multiplied by its pure vapor pressure. So we can find the vapor pressure of any individual component
Yes.
as long as we know its mole fraction and its original vapor pressure. Or there's 3 terms here. Any one of them that's missing, we can find. So, the pressure for butane in the mixture is equal to the mole fraction of butane in the mixture multiplied by the pure pressure for butane. All right. So this number is the 698. This number is the 0.423, and this number is the pure value of butane. There's 3 terms, 2 numbers. Solved for the time. This number is equal to that number multiplied by that number, which means that this number divided by that number gets to be equal to this number. And that has no units, but this one does. So we get to keep the units that that quantity is in.
1650.
So, in its natural occurring state, at whatever temperature this is, what state of matter is butane?
Is it a solid? Gas.
That number, its vapor pressure is larger than atmospheric pressure, which means all of it has boiled. It is way past boiling at the temperature in this question. It's a gas. It's a gas that's dissolved in the liquid, but it's still a gas. Okay. Questions? So we have a very high vapor pressure. That this vapor pressure is above atmospheric pressure. Which tells us this is a gas at surface temperature. There was a bit that if we had an extra day, we would probably look at osmotic pressure. Because that's a thing. Our nursing students need to know about osmotic pressure.
Is that pressure within a liquid?
Yeah, so osmosis is a
Yeah.
diffusion effect, but it's the reverse way of how we normally consider diffusion. We normally consider diffusion as being an entropic event where it's just more probable that objects diffuse away from areas where they're in high concentration. Osmosis is for solutions, and it counts the water moving, not the solute.
Yes.
So it's the same general principle, but it's defined in the using the reverse
Yes.
language
Yes.
than diffusion does.
Okay, that's it. Great.
Okay. Let's give you one of these.
Colligative properties, the ones that show up in general chemistry, are elevation of boiling point, depression of freezing point. Those are the big ones. And depression of freezing point and elevation of boiling point is all about vapor pressure. So let's look at the vapor pressure lowering of a solvent due to added solute. When you add a solute contaminant, you are basically blocking the path. It's almost a physical property here. You are blocking the path of evaporation of the previously pure material. Here's a question. If I add 114 grams of sucrose, you know what the formula mass of sucrose is?
Fructose.
It's a fructose and a glucose
Oh,
stuck together.
formula.
So we use a water. Each of those is C6H12O6. Stick those two together and lose an H2O.
So that'd be C12,
This is a vapor pressure lowering, depression of freezing point, elevation of boiling point, all of those things, colligative properties, only depend on amount. They don't depend on identity. But the amount that they depend on is mole amount, not mass amount. And if we can figure out vapor pressure lowering, then we can find the number of moles. And if we find a number of moles, we can backtrack, because there's a mass,
Yeah.
to find the formula mass. See what we can do. So, the pressure due to the solute is the mole fraction of the solute multiplied by the pressure of the solvent. We'd done this on a previous occasion. So there was something not specified in the question that perhaps we should go back and revisit. Sucrose itself has no vapor pressure. So you can't find the pressure due to the solute from the vapor pressure of it, because it doesn't have one. It's only the solvent, in this case, that has vapor pressure. It's the water. Okay. All right, so the lowering end of the vapor pressure is due to the sucrose. So, how should we lower it by? It went from 17,540 to 17,435. 1 point what?
0.10, sorry. 5.
There you go.
Is that in UK?
Those two numbers are the same.
So that's kind
If you had $540 and then you went shopping and you have $435, how much would you spend? Do that in your head.
I can, I just choose not to.
So this is the value of the effect. This is what this is doing.
Okay.
Okay? And it's equal to the mole fraction multiplied by our original value. So we know that this original value here is 17,540 when it's pure. Okay? And what is here is the moles of the solute divided by the moles of the solute, plus the moles of the solvent.
You have to find that one.
Do that one first. These two, that's what you're going to find out at the very end.
Yeah.
But we're going to help you. But that one's actually in the question. That one, the moles of the solvent is the mass of the solvent divided by the formula mass of the solvent. And the solvent is water, and there's 1,000 grams of it. And H is 1.008, and O is
15.999.
I just say 16.
yeah. Uh-huh.
It's just more fun.
1,000 divided by 16.
That'd be 18, right?
Oh, it is. By 18. This is 2 hydrogens and 1 oxygen. 55.55. Which is the question, which is the answer to the question, what is the molarity of water? Because molarity is how many moles are there in a liter? And a liter of water is a kilogram-ish, depending on the temperature. And the formula mass, 55 mole, 55 and a half mole. There are 55 and a half moles of water in every liter.
Wow.
Yeah.
Nice.
Okay.
I'm sorry, I just like, huh?
Concentration of water doesn't make sense. I guess because there's a solute in there that's already in the concentration of water.
Squeeze up to 55.
You've got some rearranging to do.
Yeah, we do.
We do.
Let's just collapse this.
Just divide by 17.540.
Let's first do that.
Multiply the other thing, but you can't do that.
Well, you
Doesn't
can.
make-
You can.
You can. But then when you just.
I think you can. I didn't 100% hear what you said, but I think you can.
You can. We can. It's.
It just feels like there has to be.
So there may be more than one procedure for doing it, but I see a division and I want to get rid of that.
I do too.
So I would take that over here
Mhm.
and multiply everything on this side by that term.
Yeah.
So you have a percentage of it.
And then I have this number minus another number
Yeah.
equals that number.
Yeah.
But and I've got a solute and a solute on both sides, and then I would probably divide over this way, and then I would subtract. Does that make sense?
Yes.
Okay.
Like I picked up.
Do it. Do it and let's see what we can get. And while you're doing that, I will try to draw sucrose. Sucrose is a glucose. Well, I could draw it if it's not in the Howarth projection.
Oh, you're gonna do a Fisher projection? No. Can you do a Fisher projection?
Yeah. We don't normally do them for disaccharides.
I didn't think we did.
Okay, so the question is, I think that they're both out of the anomeric carbon. I think it's a alpha beta 1 to 2 prime glycosidic linkage from memory. And then I don't remember if these are ups or downs.
I got a number. We'll see if it's right.
Oh. Yeah. This. Which is C6H12O6 plus C6H12O6 minus H2O gives us C12H22O11.
Yes.
Ah, feel good. No, I
Okay.
don't. No, I don't. 22.
Yeah.
12 times 12 is 144.
That's gross.
22 times 1 is 22. And 11, I see what you did there.
Yeah.
11
God,
times
I picked it up.
16 is 160, 176. Okay. 144 and 6 is 150. And 70 is 220. 320. 344. Is that your answer? How off are you?
Well, I have moles. Wait, I need to calculate the formula.
Oh.
Yes. I didn't even.
Okay.
I didn't. Yeah.
Oh, yeah, for letting
I found the moles.
You get 3, 3, 4, plus 3, 3, 4.
You have moles, and we have grams. Grams in the question. So, this will give you a number that's in moles, and we'll revisit that in a second. And then moles is mass divided by formula mass, which means that formula mass is mass divided by moles. Yeah. Grams divided by grams per mole gives me moles. And the mass is 114 grams divided by whatever number of moles we got here.
Oh wait, we got pretty close.
Probably get about 340.
Yes, that's what I got.
I think you can safely get within a percentage or two of it. Okay, so I don't know how you did it, but what I would do would take this term, pen's running out. When the pen's run out, that's the end of the term.
Amen. I'm sorry, excuse me.
0.105 multiplied by the n solutes plus 55.55 equals n solutes. It's like being in high school, 17.54.
Not the high school.
Not the high school.
Why, Dr. Bob?
Wait, how?
Why are we in high school?
Algebra?
Just rearranging.
Oh yeah.
You scared me.
I was like, I hope
Don't
she's
take me
back.
back there.
Yeah, no. Okay, which is 0.105 multiples of n solute plus whatever that number is,
Yeah.
What it-
5.83.
5.83, sounds reasonable,
Yeah.
equals 1 L solute multiplied by 17.54. Okay, the next thing I would probably do would be divide.
Yeah.
I usually try to get rid of those first.
Yeah.
So if I divide that by 17.54, it makes that go away. Okay. So now I have a new number here and a new number there. What is 0.105 divided by 17.4? 17.54. Is this not how you did it?
No, I just subtracted over.
105
Okay.
It was
That way, you that way you could just divide the numbers and not have to worry about dividing
Okay.
the variable.
I just erased it, didn't I?
Yeah, you did.
So I had 0.105 numbers of n solutes
plus 5.
plus
5.83.
5.83 equals this.
Yeah, that part. And then we just subtracted over the variable part. Kind of imagine it like an X.
Okay, so you take
You see what we did? Made it a variable.
17.54.
The poor pen.
So the semester is over.
So 70 point, yeah, this is it, this is easy.
This is less.
17.54 n solutes minus 0.105 N solutes is now equal
There.
to 5.835.
Yes.
And 17.54 minus 0.1.
17.435.
17.435 N solutes is equal to 5.83, and therefore 5.83 divided by 17.435 is the value of N solute,
Yes.
which is equal to,
0.335.
okay,
And then divide that by that.
grams per mole gives me an answer of about 350.
40.
Oh, wait a minute. That's not grams per mole. I've already done
I know,
that.
I did the same thing. I put grams per mole, I was like, no,
It's
she's
now
not.
grams per mole. Alright, which kind of matches
Yeah.
what my chemical knowledge of sucrose is. It works.
Woo! Hallelujah.
And with that,